Hello, this is David Birch at Star Path School of Navigation with a note on several things. It started out being a note on dip short. Dip short is a technique that's used in celestial navigation when you somehow end up in near land and you don't know what land it is. If you've had let's say you've had very poor navigation for a long period of time and you somehow end up on land, near land, and your first fix is or first sights are maybe a sun and it came up over the land. This could happen maybe if you came up on land at night and then hung out till the morning, so forth. So this is a trick that's kind of deep in the navigator's bag of tricks, but it's good to know, and the solution of it brings up several points that you have to kind of all pull together at once. So if the sun were out here and here's a real ocean horizon over here, then you just use your normal dip. The dip's accounting for how far we're seeing over the horizon. When our eye height is above the water some number of feet, 9 feet, 10 feet, then we're seeing over the horizon. We would see the true sea horizon, which we would see if we were floating eye level in the water. So we have to make that correction. The angles are too big. The angles that we measure with section are always too big, and we have to correct for the dip. Now when we end up in a case like this, where here's the land is here, then this is even it's even much shorter. I mean, it's the horizon is closer to us and the correction's even bigger. The typical, and you can generally tell, this technique is used these days. It's not used very often at sea, but it's used a lot on land when you're practicing your celestial navigation sights on a lake or on a bay that's close, and you're using the shoreline on the other side. Then you can use this dip short technique, and it works very well, and you can practice just like you're in the middle of the ocean. It's much better than practicing with artificial horizon. So we use it in practice all the time, but here's a special circumstance where it might come up at sea, and it's nice to know how to solve that. And so that depends on your eye height, not the sun height, that's the sextant height here, and then it depends on your eye height, and then the distance you are from the shoreline. Now you can estimate, we know what the normal dip formula is. The dip formula is the square root of your eye height. So if you're 9 feet above the water, you take square root of 9 is 3 and convert that and call that nautical miles. So if you can judge, like let's say you're 9 feet and then you judge that the horizon is more than 3 miles away, then that's fine. You can just use it as is. Even though you're using a shoreline, it would be just it's actually you're not seeing the shoreline. The curvature of the earth is cutting it off. So you have to judge that. So here our ship came up here, and we don't think we're we're, let's say, 9 feet above the water. I got this morning sun sight to take, and we feel we're closer than 3 miles. Now the question is, how far off are you? This is land. You have no idea what it is or where you are. So that's that. So the next step here, so the first step you do is take a bearing. Pick a landmark that you can identify. We don't know what it is. It could be a rock or just some change in the shading or a group of trees or something. So you take a bearing to that, and let's use true bearings for this, and let's say that was 347 true. Then what we have to do is move. So we have to move. Let's say we're going to drive this direction, and we want to move until that bearing changes by at least 30 degrees, something like 30 degrees. It's not crucial, but we want 30 or more. And so you do that, and you take off, and you move, and then you move over. And here in this example, we're going to assume that we went on course. I have to see what the actual course is that was used here. I think it was 294. So we were off. We headed off on course 294, and we noticed that after traveling 0.6 nautical miles, that the bearing changed to 012, and that line of position is plotted here. So, and also we just assumed here that the top of the chart is 00. So this is like a compass rose, and we use a protractor to do these scales. Now with these two lines plotted relative to our unknown landmark, or it's identified but unknown right here, now we can figure out where we are, because we know we went 0.6 miles in direction 294 to get from here to here. So now we start our plotting, and for this now we're going to have to take our blank. We're doing this on a blank sheet of paper, so just forget this little drawing here. Just pretend that this is just a dot on your paper. This is a blank sheet of paper. There's a dot here, and you drew your two bearing lines off from that dot. And so we had to make a scale to call 0.6 miles. We had to make a scale. So pick any convenient scale at all here for this vertical scale, or for the distance scale on the chartlet. Now, so here's the reasoning. So first let's look at the reasoning, and then let's look at an easier way to do it. Let's say let's guess. I know when I took my first LOP that I'm somewhere on this line. I know I was somewhere on this line before I started moving. Then I sailed 0.6 miles in direction 294, and I ended up on this line. So now where am I? Well, let's say I assume I was here. If I started here, I went 6/10 here. That's no. I can't be there. I wouldn't even get to the other guy. A is wrong. B, let's say I was at B. So B, I went 0.6 miles. I ended up here. No, that cannot be it, because I've already crossed that. There's only one place here on this diagram where you can start here on this line, go 0.6 miles in that direction, end up on this line. And when you find that, you've got your position. That's called a running fix. But notice here, these dots all line up. So that brings us to the normal way you would do a running fix. You wouldn't hunt around, peck around like that to try to find it. You would just go on your diagram, or in normal navigation, you do this with a chart, and that could be a light. For example, it could be in the fog. You're on a chart, you know where you are. I mean, you know what region you're in and everything, and you see a light, you can even identify the light. But that one light shining through the fog is all you've got to go by. So you do a running fix to get your position. So the way you do it systematically is you just take any point A here, draw a dot, then draw this 0.6 miles, do your distance run between the two sites, do your distance run in the right direction, and put a dot. Now you take your parallel rulers and just move this line over to here. So we're not hunting around, we just pick any point, draw the 0.6 in the right direction, parallel rulers here to here, and where this crosses this, that's where you are, and that's your running fix. Now, with that done, we can use our scale that we use when we as soon as we called that distance 0.6, we had to have in mind some scale here, which we made, some convenient scale. Now you use that scale to measure this distance, and that's 1.1 miles. So that's a part 2 of this dip short business. We now know how far off this land we are. We don't know where we are. We have no idea where we are. We don't know what that land is. But we do know we're 0.6 miles off that landmark. Now we can go just to carry on here. And now these are just the formulas. This is the dip formula that's used in the Nautical Almanac. There's a dip table. That dip table is nothing but solutions to this. So if this is 9 feet, square root of 9 is 3 times 0.97. So the dip correction for 9 feet is 0.29. 81 feet is that. Here's what we measured in this example. And the dip short formula is this. That is not in the almanac, but it's in our textbook, and I'm sure it's in Bowditch somewhere. It's various places. That's the formula for the dip short, where this D is in nautical miles and this HE is in feet. So if you're in Europe or something, you have to convert this feet, your meters to feet. But anyway, there's the formula. So now we put in our 1.1, our 9 over 1.1, and we get these two. So the dip short is 5.1. So we're still standing at 9 feet. So if we were looking at the real shoreline, we would use a dip of the real true horizon, we'd use 2.9, but up in this dip short case, it's 5.1. Both of these are negative corrections. The sextant height we read is too big by this, so we have to subtract it out. And let's see what's left here. Okay, so this is just a last schematic to show what we did. This is the true sea horizon hidden by the land. That's where we should have measured and used a 9 feet dip correction from right out of the almanac. Since we're taking sights to like here, below the land to here, then we had to figure this extra dip due to that. That's called dip short of the horizon, or dip short. And that is the exercise and solution.